DraftScience video with a cigarette, which, makes me so much more, yeah, nothing. Relaxed anyway. Chemistry. Anyway, on to the subject, which is gravitational lensing. And the idea of proving theories and blah blah blah. So the idea is that relativity, general, is proven by gravitational lensing. So this is one of those things where, there's a whole dramatic story about how nobody was paying any attention to Einstein, he didn't prove anything, and blah blah blah. But when they found gravitational lensing, because that's what he predicted gravity would be bent by, light would be bent by gravity. So this thing that's going the speed of light, really high velocity, and has, by everybody else's accusation, no mass, is bent, is changed, is affected by gravity. Because gravity isn't gravity, gravity is a bend in space, and even light can't resist the force of the bend, or something like that. Well, anyway, enough of that critique. So anyway, from my perspective, there's no room for light being bent by gravity, because light is gravity. It's the same mechanism, same functional bit. And the bits, gravity doesn't affect gravity, so to speak. The force carrier, the quanta, just doesn't work that way. You can't you can't truly change identity. I know it's a better way to say this. It's the direction of things that creates these dents in space. This is a convergence of stuff from the whole universe, and it's converging in one place. And that's something you sort of have to understand, is that, the stuff that hits you, let's say if you were in a pressure field of these directional arrows, the truth is, the stuff that's hitting you, okay, is way far away, was at one point, and it's made a long trip to get to you, and as it gets closer and closer, the little individual bits, it gets denser and denser and denser. You can sort of understand that it's this thing, this hand thing. As it gets closer, as the mass gets closer, it's more compressed. Everything's closer together. It's a much more dense thing. Well, anyway, so that's the convergence. It's not exactly the way I wanted to put this, or how I wanted to get to this. So anyway, so the Miles Mathis guy has a pretty good, I'll leave a link to it, a description of kind of some of the flaws of what's being stated as a proof. And yes, Miles Mathis is seems not to be an entirely genuine human being and all that kind of stuff, and lots of truth or kookery there. But I'm just saying that this article hasn't been critiqued as far as I can find anywhere, and the bottom line conclusion is the same as my conclusion, that what we see as lensing is the consequence of dust. It's gravity coalesces stuff around it, and it is the stuff around gravitational bodies that are creating diffraction. So that's the key word he uses, is it's diffraction. Lenses are diffraction. Everything's diffraction. There's no bending by any other force, but encounters with things that have an orbit, that's the way you change direction in any real sense. You can't change something's direction unless you catch it in an orbit and fling it in another direction. That's it. There's no other free lunch. Every other way you have to stop it and turn it around, or point it somewhere else and then push it. There's no free way to change a direction except through the use of diffraction, allowing, this particle anyway, force diffraction. Force diffraction, I guess, is a way of saying it. But we're always going to have this problem with how to describe the quantum, as we have too many broken words. Even the word quantum is broken by quantum mechanics and the traditional understanding of that woo-woo. The word wave is totally ruined, because now everything with a frequency is called a wave. There are lots of people talk about gravitational waves, and what they're really talking about is the frequency that would be created if, say, something was orbiting something caught in one of these gravity wells, and the fact that it would have a closeness and an awayness and be blinking in terms of its gravity would be higher when it's perpendicular and lower when it's horizontal, you could argue. And so two highly gravitational bodies could be spiraling into each other, and they would call the fact that there's a fluctuation in the intensity of the gravity, that they would be, like I said, when they line up, there'd be stronger gravity than when they're across from each other. That's a wave, when all it really is a frequency. There's a period. It's a periodic emission. Now every periodic emission is going to be called a wave with the new physics, which I think just breaks the word. Alright, still not getting to exactly what I want to say here. Alright, so I was, this is sort of like an important subject, and the Wikipedia article is, minute. Let me shrink this window. I don't know. Wikipedia is not designed very well. It's a tiny amount of description for such a big subject. I mean, it's just, very, very little is written here. Very little evidence that's of any real value. They have artistic renditions, right? So you can watch artistic renditions of lensing. But anyway, so I wanted to get to this new famous one. So even this is a maybe I'll make it bigger just to ease of photography and such. So this is how they draw Einstein. When the Einstein bit of the one they did in, like, whatever, 1910 or whatever the hell it was. So there's an eclipse of the sun, and then there's lensing because of the gravity near the surface of the sun. So again, understand, Einstein wouldn't like this drawing, because the lensing is happening really close to the sun's surface. And so look at the way they drew this. First I don't know what this is, this hollowness, and the idea is that there's something behind the sun, the light comes out, it gets bent, and it goes to the earth. Well, in this case, we're talking about the sun and a very, very distant object. So first, this is way off in the sense they should have at least expanded this distance. This distance should be much larger than this distance, at least implying that. And obviously this is a surface phenomenon. It doesn't happen out here. It only happens at the strongest gravity. So right here on the surface of the sun, gravity is 28 times the strength of gravity on Earth. Which doesn't sound all that big, considering the sun is, I think, 380,000 times as massive as the Earth. So I guess you could fit 380,000 Earths inside of this the shell of the sun. So you would think it would be higher than just 28 times, but you have to think about the fact that there's a huge amount of surface area that's now 28 times the gravity of Earth. It's not just that you have 28 times the gravity of Earth on just something the size of the Earth. You have a huge amount of gravity expanded to a much greater diameter. And, that's where this sort of gets important. Alright, so, like I said, this description is just not very good. And it certainly doesn't imply the very subtle bending that took place right at the sun's surface. So even at the surface of the sun, at gravity that's 28 times the strength of the gravity on Earth, the bend was very, very slight. And so that requires the distance of this galaxy to be tremendously huge. Alright, so there's lots of bad images here, so I might as well go through some of them. This is called the Einstein cross. They say this is gravitational lensing. All four of these objects are the same object behind something in the middle. And you can see some parallel between, like, these two objects have a parallel shape, parallel malformation. But it's almost inverted. See, these two are flipped this way, where these two aren't flipped at all, going this way. Now, what sense does that make? Right? I mean, these two are like obvious mirror images of each other, and yet somehow the mirror broke here. Because these two are, well, I suppose this one's facing this way, and this one's facing this way, this one's facing this way, this one's facing this way. So they're both broken in the same ways, that they're not proper reversals of each other. Yeah, technically, well, point for a later time. Yeah, I'm just now I'm starting to look at it, study it. But anyway, point is why that configuration. There'll be lots of questions to be asked about why they aren't here and here, and why they're uneven or imbalanced, because gravity tends to do this balance thing. Anyway, so yeah, I don't want to get lost with that image, so let's start back at the beginning. That's just showing preventing the sun. You had to block the sun so you could see the gravity. Alright, these are the more famous images, where you have this lensing, they're arguing, that's taking place, and you're huge distances from what is supposed to be the object creating the lensing. So the strong gravity is here. The strong gravity isn't out here. So this is why they invented dark matter. They had to come up with some explanation for this field being so dense that you have a strong enough gravity here, at least 28 times the Earth's gravity out here, to do this refracting, or this bending of the light through the gravity that it's traveling through. So just understand that that means you have to have mass to create that kind of gravity. And there's no indication of mass in there. So this whole idea of dark matter isn't just dark matter. It's supposed to be some kind of matter that's invisible in every other respect. So it only shows up to do lensing, and it only does lensing when it feels like it. You know, not in every circumstance where you would expect it, but just now and then it does this. Occasionally it poofs a lens. You know, which again just makes this thing sound like these are obvious questions you'd have to ask. If this lensing was really taking place and there was really that strong a gravity out here because of dark matter, then we would be seeing lensing all over the frickin' place. There'd be lenses all over the universe. It wouldn't be hard to find at all. So that's what makes all this a lot bogus. Alright, so let's go through some of the others. The artistic rendition. So again, you have another example. So this one's more like a black hole, and so you could argue that maybe the strongest gravity is out here at the rim, but again, it has to be at the rim. So I mean, this is something even said on the Wikipedia page. So I'll show you I load images, so I have to go back. Well, let's finish the images and I'll get to that part. So here's supposed to be another lens here, and another lens here. So again, this is a field that looks pretty vacant. You have one center object, presumably, and this would have to be the strongest gravities here. So even though you have no mass here, apparently, you can see right through all this, so there's no mass, yet you're creating this incredibly strong gravity out here at this rim. Presumably the gravity starts getting weaker out here, and it gets weaker going in, under any kind of normal rationale. And what would be the explanation for that? There clearly appears to be much less mass in here. So why would the gravity get weaker as you go in past this line? Why is this line the strongest gravity? Now, I don't think they have an explanation for any of that. You know, these images are just so nothing that you barely can't make anything out of them. So they talk about weak lenses, you know, lenses that you can only figure out they exist because you have 17 images from 14 different telescopes, and then you figure out that there's a slight shudder in the images, and therefore you call it lensing. But again, it's, who's fooling who, what, where. So again, these are all made out to be as if the lensing has a perfect spherical shape, so somehow the lens has to be spherical. It has to be being created by a convergence, so the gravity has to have this even line, presumably, and yet there's no indication of any even gravity in this field at all. This is not a sphere of matter. So how is a non-sphere creating spherical gravity? Gravity that's equal in all places. It's not possible. Again, unless you accept this notion of pockets of dark matter. I mean, it can't be just everywhere dark matter in some sort of smooth amount. It has to be just pockets of dark matter, and that these pockets just coincidentally happen to be where their lensing is, and that they in no way affect any other function of the area. So again, this is presumably lensing all these little swirly, you can't really see it, but some of them are stretched, little streaks here. This is all supposed to be something behind all of this stuff, many billions of light years away, that you're seeing as bent light. And yet, what's the explanation for that being the highest gravity? When clearly you would presume that the highest gravity would have to be somewhere in here, if you were to presume. And you'd also have to say, if there was a gravitational sphere of that strength, of that size, in this area, that stuff would have to be pulled into it. There would be obvious expedient migrations happening around it. It would be like a sun in its field, and it would be consuming the field around it. There's no denying the sun consumes. It does. I mean, clearly, as far away as the Earth is, as weak as the gravity, so-called, is, it's that there's enough density of that gravity to take something as massive as the Earth and say, we're not going to allow you to keep going the direction you're going. Even though you're moving fairly fast, and you're really massive, we're going to turn you around. So even though it's the gravity here from the sun is supposed to be like what, some like 0.006% of the gravity at the surface. I mean, come on. I don't know what that was. You don't really know what that is, but it's such a nothing image, and it's got all kinds of different artifacts in it, and you'd have to go through it and analyze it and say, what the hell are you talking about? So anyway, so what did I wanted to go back to the page and just read the littlest verbs here. I'll have to go all the way back through the images. Why can't you just take me back to the Wikipedia page? God, browser. Wikipedia for the encyclopedia, that should do it. Didn't do it. I thought if I went all the way back, I would have gone all the way back. Ah, there we go. Oh, Jesus. What the hell, browser? So if I go to this page, it jumps me to that page. I wonder why it's doing that. Very, very obnoxious of you. There, okay, stop. That's where we want to be. Sorry. Alright. Unlike optical lenses, maximum bending occurs closest to and minimum bending furthest from the center of a gravitational lens. Unlike optical lenses, maximum bending occurs closest to and minimum bending furthest from the center of the gravitational lens. So just to understand what they're basically saying there is that, again, here at this surface you would expect the highest gravity. You wouldn't expect the highest gravity way out here. This is like somebody arguing that the highest gravity of the sun is somehow out here where the Earth is orbiting. And that doesn't make any sense. And again, dark matter would have to not only be dark matter, it would have to be incredibly massive matter to account for us achieving some kind of gravity like that. And there's no way to account for the fact that, again, it's not how gravity works. Gravity will consume stuff, and velocity isn't that easy for matter to acquire, as strange as that sounds. But I mean, that's what you're doing. You're basically, when you have velocity, it's because you're consuming it out of the field, so to speak, and it's not easily created as a thing. Okay, it's because it has to be filtered, and filtering requires a great deal of time. The universe takes a long time to filter out of itself, out of the field, this condensation. All right, so let's go to this space.com. So here's this new one they found, which is a galaxy, you know, very far away. And here's the native image. So you sort of have the idea of the image of the galaxy here, and then it gets bent here, and then, you know, it gets indescript, and then you can see an image of it here, and you see a little image of it here, and then you have some of it happening out here, and in strange lines that don't make any sense. They're very uneven to what's supposed to be spherical gravity. So the idea is there's a star cluster here, and that it's creating enough gravity to bend light from a very distant the galaxy way behind it. And it just happens to be the brightest galaxy ever seen. So it just happens that the brightest by 3 times galaxy that exists in the known universe just happens to exist behind a field of stars, and it's being lensed. We wouldn't be able to know it was there unless it got lensed. I mean, doesn't this, it just sounds a little too convenient, doesn't it? A little too convenient. So anyway, here's the image they drew of this. And so it just, I mean, it's just sort of important to understand that by Einstein's theory, you're technically supposed to have a sun here. Some massive body full of mass, and it has very strong gravity on its surface. So it doesn't have strong gravity out here, and it doesn't have strong gravity in here. It has strong gravity on its surface. That's where the strongest gravity is on the surface of gravitationally relevant clumps of matter. So the argument here is that this circumference somehow must account for this very strong gravity at this point. And again, so that's why they invent dark matter, because they just basically fill this whole circle full of this invented dark matter and just say the dark matter is doing it. Well, again, then explain why the dark matter isn't this big or some other size, and then explain how the dark matter is completely transparent, how we can still see things through this star cluster that might be 1 billion light years further away. We can't see the thing 15 billion light years away, but we can see things 5 billion light years away behind it, so we can see through dark matter. There's no evidence that any of this dark matter creates something like dust, where it would actually obscure visibility. So, where's the explanation? Where the alternative explanation is that, yeah, anything that's a little bit dense here, there's lots of clouds of particles in the universe, lots of nebulous blobs of still unformed, still uncaptured little bits, and that these would be little bits that are circling because they're like the asteroid belt or something. They're trapped in the gravity. It's strong enough to trap these little tiny bits that have very low velocity, but it's not strong enough to do anything else with them. So they just sit there and orbit the gravity, the collective gravity of this object at this distance. Because if they were closer, they'd get sucked in. And if they were further away, they would float away. And so they're in this area where they're neither too big nor too small. They're just right for the amount of gravity of this area, and so they stay where they are pretty much. And that's, you end up with this tendency for gravitational objects that have been around for a while to basically clean the space around them. If they've been around for a while, they clean all the little stuff that's close, and the stuff far away keeps drifting away, and the stuff in that middle range, yeah, it gets caught. So anyway, and with the appropriate velocity, of course. So is that all I wanted to say? Yeah, so I think there's lots of room to doubt that this lensing thing is a real phenomenon. There's very little science given in these explanations. There just isn't. You know, very little, hey, here's a place that looks exactly like that place. How come it's not doing the same thing? Here's a circumstance exactly like that circumstance. Why isn't it doing the same thing? Why isn't there lensing all over the place? Would be I think, the logical question to ask. There's lots of eclipsing going on in the universe. Lots of opportunity to block out light that's giving you a hard time in seeing. But this is another thing, right? Gravitational lensing acts equally on all kinds of electromagnetic radiation, not just visible light. Weak lensing effects are being studied in the cosmic microwave background as well as galaxy surveys. So again, their argument is it's bending radio waves, it's bending microwaves, it's bending light, it's bending gravity is doing this. And I call bullshit. And I certainly say that bodies like the sun, who are producing mostly light, why should the light be of any consequence if you're detecting X-rays? It won't affect your X-ray detection at all. So if X-rays are being lensed, there should be plenty of points where the sun crosses, you know, in the sky, so to speak, in the field, where the sun and our alignment are such that an X-ray source goes right behind our sun, and we could clearly observe any lensing. Where are those pictures? Oh, yeah, they're not here. So anyway, so this is the problem, though. Physics is so deep in terms of the number of phenomenon that are studyable, right? I mean, now they've done the standard model thing, come up with quarks and muons and gluons and puons, and you know, they've even resurrected a bunch of Star Trek ideas of, you know, what the hell is the warp engine made out of? Yeah, they've made those up. You know, they just create all these phantom, or you know, these studyable phenomenon, and they have this little bit of evidence, and then they create a whole field of study, and it's like, you know, it's so hard to get to the actual evidence, the actual thing for which the experiment or the conclusions are based. And it's kind of like the two-slit example, where the most popular video explaining the two-slit experiment, Dr. Quantum, cites experiments that never took place. They're just complete phantoms as evidence, you know, of the turning the detectors on and off, and not recording the tape or not looking at it, and therefore you get a different result if you look and if you don't look, and all, you know, just made up. No evidence that anyone's ever done that experiment. You know, and that's what you're stuck with. And so, you know, to debunk this, you have to do this whole thing where you start analyzing all these raw images to figure out, you know, what's really happening. But instead you get these cartoons, you know, of artist renditions of reality. And, you know, it's just wrong. Interesting. I don't know why they're using two things spiraling that have tails. That doesn't make much sense, but whatever. Who cares? It's better not to ask why. Ask why. Yes, you're not going to get the right answer. I don't know. I didn't see this video, I don't think. So, looking further into the past. Foreground galaxy, background galaxy. And this is some sort of, I don't know what this is. Here's our radio telescopes. So here's the foreground galaxy. See, again, we have the strongest point of the gravity is implied to be not where the matter is dense, but where the matter isn't dense. So again, Einstein was talking about the surface of the sun refracting light, the strongest gravity, not 100 miles up, not 500 miles away, not 1,000 miles away. No, the surface is where the strongest gravity is. And you need the strongest gravity because light is tiny and moving really fast. And to bend it, you're going to need one hell of a strong gravity, and that was the theory. But again, the theory doesn't, in my opinion, you can just see how this math is cooked, because you can't give photons a mass of 0 and make this work. You just can't. And by obeying any kind of rational rules. The trick is that gravity is a little bit tricky. Again, because gravity is an induced force. So imagine this was just circling this. You know, these things, gravity doesn't exist until you induce it, until something of mass creates acceleration in the other thing, and then the gravity grows in it, so to speak. You know, it feeds. It's a feedback loop, gravity. And like electricity and magnetism, the field is one that's induced. You know, the other trick is that the sun's gravity, that is the pull on this object, they're sort of independent, completely independent of each other. Yeah, the net result is there's going to be a total attraction. But we know that this body isn't really going to move towards this one at all, and that this body is going to do all the moving towards this bigger one. We know that's going to be the end result. And the reason it's going to be is this body is just going to spin to create acceleration, where this body is going to move to account for its acceleration because it's being dominant. It's being dominated by the stronger gravity. But the two gravities don't really work with each other at all. This one is completely independent of this one. So this one creates a gravitational force on this object creates a gravitational force on this object. So the force is this way. This gets pushed by this is the gravity difference, the imbalance created by this gets pushed by that. This gets pushed by the gravitational force caused by this. And there really isn't anything else. There's no combining of them at all. And that's where it gets a little tricky, like the same things of the same mass fall at the same rate to Earth, because it's the only thing that's relevant is the Earth's gravity. The gravity, the weight of the individual objects is irrelevant. Their gravity isn't relevant because the Earth will not move towards the object that's falling. It's not going to do it. Some tiny portion of the Earth will move towards the object, but the Earth itself will not. And so there'll be no translation of Earth movement in space commensurate with any kind of gravity. But regardless, the two are completely independent. This thing's gravity affects this thing's gravity affects that, but they don't combine as a force at all. They're a completely independent phenomenon, beyond the fact that they are induced in each other. So once it's induced, it's completely an independent function. But again, this whole argument of here's the image of the lens. So again, the strongest gravity is here, and yet somehow the lens is creating the diffraction way out here. And as it states in the Wikipedia article, the strongest lensing has to be at the strongest gravity, not at the weakest. This is very weak gravity. So the only way they can make this work is they're claiming this area here around this object is full of a dark matter that's as dense as this object. So this dark matter somehow has the same mass as this object here in the middle, and now this whole planetoid or this whole sunoid or this whole dark it's not dark, right? I mean, they call it dark matter. It's not dark. This isn't blocking anything. You can still see through it. It's not dark. It's invisible mass. See, if they said invisible mass, then everybody would say, what? What are you talking about? I mean, okay, I went with the bent space, I went with a lot of this stuff, but now you're going to say it's invisible mass? Oh, come on. Does that really work for you? No, come on. Anyway. Alright, well, I didn't do as good a job as I wanted to, but I just want to get to the point that if you read the Wikipedia page, I'll link to that, and I'll link to the Miles Mathis article, if you're all interested. I mean, you know, obviously it's just one obscure little piece of stuff, but again, it's used as this lensing thing is about one of the only proofs there are that's anything real for this whole relativity crap. So, you know, it sort of hinges on this in a very big way. Just trying to think of what else might, I mean, they do mention GPS, but like I said, GPS just hinges on, you know, I would argue on velocity and, you know, atomic metabolism, and so I think there are clearly better explanations than relativity for that phenomenon. Well, there has to be, you know, to use like an Einsteinian observation. There's like a quote from Einstein in here. It was just kind of funny. You know, like, what if, you know, he was asked, what if this experiment back in the 30s or whatever it was, or 30s, whatever, that was supposed to prove lensing, what if it didn't prove it? And Einstein quipped back, you know, well, then God's an asshole because it's right, or something like that. I mean, he obviously didn't say that. That's my, yeah. Then I would feel sorry for the dear Lord. The theory is correct anyway. So that is a little obnoxious of Einstein to say. Quipping, then I would feel sorry for the dear Lord. The theory is correct anyway. So even though the evidence doesn't support his theory, he would say, the theory is correct anyway. Yeah, but anyway, I don't think the evidence supports his theory, frankly. Again, these are just misinterpretations, misidentification of the real mechanics. So again, quantum mechanics based on wave woo-woo and now invented mass, you know, this is bullshit, plainly. I mean, the consequence of this invented mass, I'm just saying, just imagine that if these suns had to be a million times bigger than they actually are, you know, they would have far-reaching consequences. They're, you know, the density of the gravity away from them would be substantial enough that they'd be crashing into each other with a much higher frequency. So anyway, we'd be able to see it. It would be happening so dramatically. The speed that would be, the acceleration that would be caused as it traversed this line would be intense acceleration at that rate of, at that level of gravity. So anyway, till next time and such, and so forth and whatnot. Yeah, I think so. I'm declaring it enough. Sorry, I'm trying a new light and it's kind of dim. Yeah, it'd be nice though, make the background grainy. Might help. So anyway.